In problem 7, we're given the definition of the Poisson bracket. For two functions f and g in phase space, their Poisson bracket is the sum from 1 to n of df by dqk times dg by dpk minus df by dpk times dg by dqk. Here, n is the number of degrees of freedom in the system. In part A, we're asked to verify some identities of the Poisson bracket. The first of these is that the Poisson bracket of any two generalized position coordinates qi and qj is just 0. We'll begin by noting that the system's Hamiltonian is a function of all the position coordinates q1 through qn, all the momenta p1 through pn, and possibly time. Then the Poisson bracket of qi and qj is the sum over the degrees of freedom of dqi by dqk times dqj by dpk minus dqi by dpk times dqj by dqk. All the q's and p's are independent variables of the Hamiltonian, so the partial derivative of any one of them with respect to any other is always 0. This means that the first term is always 0 because dqj by dpk is 0, and the second term is also 0 because dqi by dpk is 0, so the Poisson bracket of qi and qj is always 0. We can do a similar analysis for the Poisson bracket of any two generalized momenta, pi and pj. Here, dpi by dqk is 0, and so is dpj by dqk, so again the Poisson bracket is 0. Next, we're asked to verify that the Poisson bracket of a position qi with a momentum pj is delta ij, where delta ij is the Kronecker delta function. We'll start off by writing the Poisson bracket as a sum of partial derivatives as usual. The second term in the sum is 0, since both these partial derivatives are 0, as we've already seen. For the first term, we have three cases. When k is not equal to I, dqi by dqk is 0, since these are also independent of each other. Likewise, when k does not equal j, dpj by dpk is 0, since these are again independent. That means that this term can only be non-zero when I and k are equal, and when k and j are equal. From this, it immediately follows that if I does not equal j, the Poisson bracket is 0, since k can't be equal to both of these at once. But what about when I equals j? Here, the sum reduces to just one term, dqi by dqi times dpi by dpi. Both these derivatives are equal to 1, so the Poisson bracket is 1. That means that the Poisson bracket of qi and pj is 1 if I equals j and 0 otherwise, and we can write this more compactly using the Kronecker delta. In part B, we're asked to verify that Hamilton's equations are given by the Poisson brackets of Q with the Hamiltonian and P with the Hamiltonian. More specifically, we want to see that the Poisson bracket of Qi with H is Qi's time derivative, and likewise for the Poisson bracket of Pi with H. We'll begin with Qi and H, and we'll write the Poisson bracket as a sum as we've done before. The second term includes a partial derivative of Qi with respect to pk, so it's just 0. We saw before that when k does not equal I, the first term becomes 0, so the only term that survives is the k equals I term, in which case we have dqi by dqi times dh by dpi. The first of these is just 1, so we're left with just dh by dpi, but we know from Hamilton's equations that this is q dot I, so indeed the Poisson bracket of qi with h is qi's time derivative. We can do a similar analysis for the momentum pi. This time, the first term becomes 0 because of the dpi by dqk term. Again, the second term is 0 when k is not equal to I, so we're left with just negative dpi by dpi times dh by dpi. The first derivative here is 1, so we have negative dh by dpi, which by Hamilton's equations is pi dot, which is the result we were looking for. In part C, we're given a position vector r and its conjugate momentum vector p. The angular momentum for this system is r cross p. If we evaluate that cross product, we see that the x component is pzy minus pyz, the y component is pxz minus pzx, and the z component is pyx minus pxy. We're asked to evaluate several Poisson brackets, the first of which is Lx and Lz. I'll write out the whole sum, which is 6 terms of two partial derivatives each. This looks a little daunting, but it's not so bad if we note that dlx by dx is 0, dlx by dpx is 0, and likewise if we replace x with y or z. That means that the first two terms and the last two terms are all 0, leaving just the middle two. If we evaluate these derivatives, we get pzx minus zpx, but this is exactly negative ly. We're next asked to evaluate the Poisson bracket of Lz with Lx. Just like last time, the first two and last two terms disappear. If we evaluate the remaining two terms, we get pxz minus xpz, which is exactly ly. The important takeaway here is that bracket Lz Lx is equal to negative bracket Lx Lz. Next, we're asked to evaluate the Poisson bracket of Ly and Lz. Writing out the whole sum again, we see that this time the last 4 terms vanish. If we evaluate the remaining 2 terms, we get pzy minus zpy, which is the same as lx. If we evaluate other permutations of the Poisson bracket of the components of the angular momentum, we'll notice something interesting. The bracket of lx and ly is lz. We can cycle these 3 around, so bracket lz lx equals ly, as we just saw, bracket ly lz equals lx, and then the cycle repeats. If we swap the 2 arguments, we just put a minus sign in front of the result. The final bracket we're asked to evaluate is lx with itself. Thankfully, this one is pretty simple. This term is the same as this term, so they cancel out. It's the same story with these 2 terms, and again with these 2, so the whole thing is just 0.